So this is, you know, quickly coming to an end for Chem 102. Next week, we have our poster presentations. So we'll see how much we get done with acid-base equilibria today. And next week, we'll probably do some acid-base titration material. And then, wrap it up for stuff that's going to be on the final exam. So next week, I've created some assignments so you have an idea of when things are due. The section 1 group is going to present on Wednesday. Section 2 is going to present on Thursday. I've made it so that your poster and your abstracts are all due Thursday morning at 9, so that it just gives everyone kind of a fair amount of time to complete those. But for you guys in section 1, I mean, if you're going to be presenting Wednesday, chances are you'll have it all done by then, but make sure and submit it by Thursday at the latest. And then, so we'll do project presentations. I initially had that due on Tuesday, but all the material will be due Thursday. Okay. And so the last week 12, your final exam is going to be on Thursday at this time, 1:00. Tuesday, you aren't required to have any lab or anything like that. So I was thinking if you wanted to, we could have an optional review session during that time. And, we can do some practice problems. We could even maybe try to do like a mock final exam kind of a thing. So looks like that sounds good to you guys. We'll plan for that, but it's optional, right? So you're not required to come and do any labs or any lectures that week. Okay. Any other questions about your project or the final, basic questions about the final before I proceed into today's lecture topic?
I had one quick question.
Yeah.
Are we going to get feedback from Erna about our abstract drafts?
Yeah, great question. Several of you have asked that. I emailed her and I asked her, to get me the list of people who submitted it. And, I would like to know when she thinks she could get that back to you, because you have your abstracts due next week. I'm still waiting to hear back from her. So yes, that's the plan, is that she'll have these for you to see in time to get feedback for your abstract. If she doesn't get it back to you, in time that you would like, I've also said, feel free to send me your poster and your abstract. I'm happy to give them a look over as well to get some feedback.
Oh, great. Okay, thanks. I just emailed it to her email, not to jump the gun or anything. I'm, just trying to get everything done soon.
Yeah. I think that, as I said in lab earlier this morning, that it's really helpful to get feedback, and it's hard to get feedback when we are doing this online class, because typically we'd be seeing each other in person. You'd be congregating before and after class and lab, and it's much easier to kind of share ideas and information that way. So since we don't have that, feel free, if you have anybody that in this class or not in this class, if you want to share it with them too. Sometimes getting an independent set of eyes that isn't even related to your, isn't even in the class is good, right? Because if you can explain something to someone who doesn't really, isn't well informed on this topic, and they can understand it, you've done well. If you guys want to do a practice presentation for somebody, family member, a friend, classmate, get on Zoom if you need to, and just present 5 to 10 minutes on your poster and just see how it works. See if they have any feedback. That's always encouraged, because as I said earlier, feedback always leads to some kind of benefit, even negative feedback, assuming it's somewhat kind in its presentation. But so yeah, email if I will to be determined with Erina. I'm hoping that she'll get that back to you in a timely manner. Send your stuff to me if you'd like me to look over it as well.
Great, thank you.
Okay. Anything else? All right. I looked back at the recording from Tuesday, and it did kind of space out at the end, just freeze. And I don't know if you guys remember, but we had some kind of notification from Zoom saying that the recording had stopped, and then it came back on. So luckily it happened at the very end, but I think I know where that started to freeze up. And so we'll just pick up from there and then progress forward. All right. So let me find that slide deck. Okay. So we were talking about strong acids, I believe that's where we left off. And we said that strong acids, and hopefully after this lab simulation, this is going to be very much more clear to you all, that they completely dissociate. And so since every single molecule of that acid loses its hydrogen, and because that hydrogen ion doesn't stay by itself in solution, it goes and forms a relationship with the water, we can say that the hydronium ion concentration, which is that relationship between the liberated hydrogen and H2O forming H3O, we can say that that concentration is the same as the acid concentration. And I think we left off with this problem. We said if we had a 0.1 molar solution of HCl, what's the pH? What's the pOH? So if the concentration of HCl is 0.1, we can also say, since HCl is a strong acid, that the concentration of hydronium ions is also 0.1. What is pH? pH is just the hydronium ion concentration taken to the negative log. So if you take the negative log of 0.1, you get 1. So the pH is 1. Now, what do the pH and the pOH have to add up to equal? Anybody remember? What's the pH scale? 14. Thank you. Right? Because the ion product concentration, or the ion product constant, or Kw, is 1.0 times 10 to the negative 4. And the negative log of that is 14. So we have this scale. So if pH is 1, then the pOH must be 13, because 1 plus 13 is 14. And then I think it froze on us and we wrapped it up, and that's where we left off, okay? So what about strong bases? What's the pH of a 0.25 molar solution of sodium hydroxide? Okay. If it's a strong base, we can do the same thing. We can say that the concentration of the base is essentially the concentration of the hydroxide ions. And so we take the negative log of that to get the pOH. And then we subtract by 14 to get the pH. So what would that look like? We could say that pOH equals a negative log of, what is it? 0.25. And what's that? What's the negative log of 0.025?
$1.6. Or no, hold on. Did that go in right? Sorry.
I got 0.6.
Okay. 1.6, 0.6. We got a tiebreaker?
Yeah, that's right. It's 0.6.
0.6. Okay. Thank you, guys. So it's 0.6 pOH. So what's the pH? It's going to be 14 minus 0.6. So 13.4. It's pH. Okay. That should make sense because it's a strong base, right? If we got a pH of 7, if we even got a pH of 9, that might be alarming to us, right? Because sodium hydroxide is a very strong base. And we wouldn't be applying this one-to-one relationship if it wasn't. Okay, so let's go do this. So let's go back to, let's do the second one. Okay, 5.0 times 10 to the negative third molar solution of calcium hydroxide. And luckily, a student in the lab today asked me a question on something similar that's in the homework problem. Otherwise, I probably would have done this problem incorrectly. So thank you for having me go over that and give you the wrong answer first so that I could then look back and give you the right answer. How would we do that? So we've got our pOH now equal to the negative log of 5.0 times 10 to the negative 3. But we don't want to stop there because calcium hydroxide has 2 hydroxide ions on it that are going, well, 2 hydroxyl groups that are going to ionize. So for every dissociation at this concentration, you're getting 2, you're getting double your bang for your buck, right? HCl, if we're talking about a strong acid, HCl just liberates 1 hydrogen, right? So it's a 1-to-1 relationship. And NaOH, 1-to-1, because it's just for whatever the concentration of that molecule is, it's releasing 1 hydroxide. But because there are 2 here, we got to factor that in. We just multiply this by 2. Okay. So I think there's a homework problem. I know there's a homework problem where you'll need to keep that in mind. All right. So then this just becomes not the -1, the negative log of 5.0 times 10 to the negative 3 times 2. And what happens when you get that?
Two.
2. All right. So the pOH equals 2. So then the pH must equal what?
12.
Yeah. 12. And that should make sense because, again, it's a strong base. So the pH should be high. Huh? Now, as we also found out in the lab simulation this week on, what was that, Wednesday and today, the pH of a weak acid isn't as direct, okay? Its concentration is not equal to the hydronium ion concentration because a weak acid doesn't completely dissociate. So if you have a certain number of weak acid molecules, only part of them are going to be liberated to form hydronium, right? So it's going to be, the concentration is going to be less. To some degree, it's going to be less than the concentration of the weak acid itself. Okay. So in this top one, we have 0.1 molar hydrochloric acid, and that has a pH of 1, right? Because it's directly proportional to the concentration. However, if we have that same concentration of acetic acid, the pH isn't 1, it's 2.87. Again, because it's not getting as much hydronium formation because it's not liberating all of its hydrogens. And in that weak acid category, there's a range, right? There's the stronger of the weak acids and the weakest of the weak acids. And what makes them stronger or weaker is their degree to which they hang on to their hydrogen atoms, or hydrogen, atoms, right? So we can't just do this taking the negative log of the concentration. What we can apply is an acid ionization constant, so Ka, which is basically like all these Ks. We have Kc, which is molar concentration. We have Kp, which is pressure constant. We have Kw, which is the ion product concentration. And then we have Ka, which specifically pertains to acids. And that's what we can use to calculate the concentrations for hydronium for weak acids, in lieu of that direct relationship between the concentration of the acid and the hydronium ion concentration. And guess what? There's going to be another K for bases. And can anybody guess what that would be?
KB.
KB, yes. The base ionization constant, okay? But nothing's changed, really. We're still writing it out as an equilibrium expression with products over reactants. And we're still going to do our ice tables and all that good stuff. The only difference is now that X isn't necessarily just simply the change. I mean, it is the change, but it is specifically for Ka, the hydronium ion concentration. Okay. And then for Kb, it will be the hydroxide concentration. So here's a list of some acids, and gives you their equilibrium reactions, conjugate base, whatnot. But in the far right, you'll see the Ka. Do you think that the Ka is larger in strong acids or larger in weaker acids? Let's look at this table from earlier, okay? What do we got? We got the strongest acids up top: perchloric, sulfuric, hydroiodic, and so on. Uh-oh. Shoot. Sorry. Somebody's trying to get a hold of me. What happened? That just... Okay. We still there? That was weird. Thumbs up. Can you still... Okay, I think I stopped sharing my screen. Let me try that again. Sorry about that. That's weird that a phone call kicked that out like that. And we are recording. Yes, we are. Okay. Now I'm going to be paranoid that my recordings are going to just stop. Okay. Here we go. Strong acids, and then it goes increasingly weaker till you get to neutral at water, right? And so what are these acids here that they're showing? Hydrofluoric, nitrous, benzoic, acetic. So it's going, if you look at this, nitrous, acetic, so on. So it looks like in this list, the top acids are strongest and it gets weaker over time. So what's happening to the Ka? It's getting smaller. So as the strength of the acid goes down, the Ka goes down. So a large Ka will correspond to a stronger acid. And when we set this up, it's again our ice table. We put in the concentration they give us. Initially, nothing is made, right? It's just at that point before the acid has dissociated. So the hydronium ion concentration is 0. Conjugate base, 0. And then we just write in the relationship of the initial and the change to get our equilibrium. Okay. So let's see what we can come up with. If we have a pH of 4.25 for a 0.1 molar solution, what is the Ka? Right. You have the reaction here. Hint, remember that pH is equal to the negative log of the hydronium ion concentration. And so they give us the pH, right? So just take that pH, convert it to hydronium ion concentration, and solve. Okay, I'll give you a minute or two to work on this, and then we'll do it together. Okay. So this is what I've got so far. I've written out the reaction. I've put in our 0.1 for the concentration. And now we just got to fill out the hydronium ion concentration. And so did anybody get that far?
So the hydronium ion concentration is going to be 10 to the negative 4.25, right?
Yes.
Okay, I get 5.6 times 10 to the negative 5.
All right. Sound good, guys? Now, something's going to be negative. Something's going to be positive. We're going to say that this side is negative, okay? Because we're going from 0 hydronium ion concentration to now gaining this amount here. Okay, we don't have any Ka value, right? They're asking us to essentially find the Ka. But if we know that this is 0, then the change is going to happen here. If it starts off at 0, meaning there was no hydronium ion production initially, and then we add this to water, and then we start getting some, and that's a positive. That's a gain, right?
Sorry, how did you get that? Oh, how did you get that 5.6 times 10 to the negative 5?
That is 10 to the 10 to the 10 to the negative 4.5.
4.25.
4.25, sorry. We take it to the, so in other words, we take it to the power of the pH. Because remember, the pH is the negative log of the hydronium ion concentration. I don't know if I'm sharing this or not, sorry. Let me try to share it again. Okay, so pH is negative log of hydronium ion concentration. So if they give us the pH, we can backtrack it by just taking the reciprocal, taking 10 to the negative power of whatever that pH is. Okay. And I see the comment, isn't there supposed to be an H2O? Yes, I mean, in this reaction, there is an H2O, but we don't consider that in our ice table, okay? Because that's the solvent, okay? So we're not going to have to assign an equilibrium concentration for water. So when we're doing our ice table, we can exclude water. But thank you for asking. That's a good question. Okay. So that's how we got this number. We just took 10 to the negative power of the pH to get our hydronium ion concentration. If we were given the hydronium ion concentration, we could take that to pH by taking the negative log of it. Okay, it's just the reverse process. And so what do we get? We get, oh no, all my markers are running low. We get 0.100 minus 5.6 times 10 to the negative 5. And then we get 5.6 times 10 to the negative 5, 5.6 times 10 to the negative 5. They're asking for Ka. So we say what? Our Ka is equal to products over reactants. Now, that could be 5.6 times 10 to the negative 5 squared, or you could write it out twice. And here, I think it's safe to say we could just write it as 1.00. Why? Because this number, 5.6 times 10 to the negative 5, isn't even going to change our significant figures here, right? So, I mean, you could do that, but it's not going to change this number at all, really. So we can just kind of shorthand it if you want. And what do we get when we do that? Anybody? 3.16 times 10 to the negative 8. Okay. Is that a weak acid or a strong acid? Well, if you look up here at this slide we had, right? We said that acids get weaker as the Ka gets smaller, and hypochlorous acid, which is the acid that we were working with, has 3.0 times 10 to the negative 8. We calculated 3.16, so we were pretty spot on, okay? That's a good check. Of course it's a weak acid because we wouldn't be doing any of this if it wasn't a weak acid, right? If it was a strong acid, we would just say, oh, its concentration is 0.1. Well, then, we don't even need to worry about the Ka constant. So these are weak acids. This is the kind of on the weaker side of the weak acids as well. Okay. So just the Ka. All right, so we did that. All right. Find the pH. Okay, so now it gives you the concentration of our acid, and the Ka, it needs us to find the pH. So let's do that. Set up your ice table. Put in your X's, solve for X, and go from there. Okay. Okay, so what's our ice table going to look like? I have HClO2 going to H3O plus our ClO2. What's the initial concentration? 0.100, I think. Yep. This is going to be 0. This is going to be 0. Let me stop sharing, make this bigger. And then we have our X's, right? Because we don't know. negative, positive, positive. So that gets to be 0.100 minus x, x, and x. They gave us, I believe they gave us the Ka equals 0.011. Okay. So so we say that this is equal to okay, sorry guys, my wife is on call, and so she's stuck with a patient, which means that I'm going to probably have to pick up my boys from the bus stop, which means we'll have to take a little bit longer break and then come back. And if you guys are free to leave at the end of class, if I have to go over a little bit, I'll just keep recording and you can watch that part later. Okay. Apologies for that. And the distraction is this is getting kind of hard to see, I think. Can you guys see this on your end? I apologize for the faint markers. But anyway, so we set this up and we get x, what is that? X squared over 0.100 minus x. All right. Do we want to do the x is small assumption? We don't have a k, or we do have a k, 0.011. Let's try it, right? Because it's always easier to get rid of an x and then find out that that assumption was wrong than to try and struggle through it the hard way, all right? So let's start up here. Yeah, whoops, I erased my expression. But essentially, 0.011 equals x squared divided by 0.100, assuming the x is small. So then 0.100 times 0.011 equals x squared. Right? And then we just take the square root of each side, and what do we get? Anybody?
You cancel out the square root with the
What is x equal? What is the square root of 0.1 times 0.011?
0.033.
0.033 is our x. Now we have to make sure that that was a valid assumption. So to do that, we take our x, 0.033, and we divide it by what we said it wasn't going to impact significantly, which is 0.100. And then we multiply it by 100%. And what do you get when you do that? Should be 33%, right? This moves the decimal point over that way and then times 100, 33%. Is that a valid assumption?
It's above 5, so no.
Yeah. Anything above 5% means that that's like the cutoff. It's saying that if it's more than 5% of that number, it will change that number significantly, so that you shouldn't just assume that it doesn't matter, okay? So that means we can't do the small x assumption. All right. Well, if we can't do the small x assumption, then this becomes 0.100 minus x, right? And then that becomes 0.100 minus x times 0.011 equals x squared. And now I think we're setting us up for a quadratic equation, right? So we distribute here, and what's 0.1 times 0.011?
0.0011.
Right? 0.0011, and then minus 0.01x equals x squared. Remember, to get it to the quadratic equation, we got to get everything over on the other side and set it equal to 0. We can say that 0.
Sorry, I think I could be wrong. I think you're missing a 1 next to the x. Is that right?
Oh, yes. Thank you. Thank you, autocorrect. X squared plus 0.011x minus 0.0011. Okay. Now we have our A, B, and C. So plug that into the quadratic equation, and we can solve. We have 2 x values, and we'll have to go and see which one's the right one from there.
As far as figuring out which x value to use, I ran into this on the IC or the homework or something, I can't remember. It's not necessarily always the positive one, right? Because sometimes in the ICE table, you end up doing minus x, so then you would have a negative concentration.
Right. Yes. So you've got to pick the one that ends up making sense at the end. You cannot have a negative concentration. That's true.
Okay, gotcha.
Okay. So we get x is equal to, what's the quadratic equation? Negative b plus or minus the square root of what? Anybody remember? You guys taking math?
B squared minus 4ac, I think,
There you go.
over 2a.
Yeah, that's it. Good. Okay. So then we just plug in our values. B is 0.011. So we write x is equal to negative 0.011 plus or minus the square root of 0.011 squared minus 4a is just 1, and c is a negative 0.0011, all over 2 times 1, because again, a is just 1. What happens when you crunch all that out? Oh, I see it in the chat. Okay, X is either 0.028 or X is a negative 0.039. Well, I'm going to go with the positive one because I don't want a negative hydronium ion concentration in this case. So we're going to go with this value here. So that's the hydronium ion concentration. How do we, what are they asking for in this problem? They're asking for the pH. So how do we get the pH? We just take the negative log of that, right? pH equals negative log of 0.028.
Don't we have to plug that back in as X? Oh no, just kidding, because it is just X. Okay.
Right. No coefficients or anything. So what do we get for that?
$1.55.
Okay. That's our answer. Now, if you want to plug it back in, it's not a bad thing to do to check and make sure your answer was correct, right? So we could say that, what was the Ka again? Oh, I guess we got to solve for the Ka. So never mind. So we could say that it was when we had our, sorry, I erased it, but we had our acid, and that leads to hydronium and this. And we said that it was a negative X and a positive X and a positive X, I believe, right? So no coefficients, essentially. So what we can do is we can say that, and then this was a 0.100 minus X, X, and X. So to find our Ka, I think they did give us a Ka. Yeah, K 0.011. So let's take this and put it together. So 0.028 squared over 0.100 minus 0.028. Because remember, we said that that X is not small enough to be insignificant. What do we get when we do this up here? Well, I don't know if you got anything, but I got 0.011.
I got the same thing.
Oh, well, why didn't you say something? No, you say everything, Hannah, but thank you. Okay. I mean that you say everything in a good way. You participate a lot. So I don't expect you to always have to shout things out and carry the class. I'm going to start calling. I think I'm going to start calling on people randomly for answers. Would you guys like that? Should we do that just to get more like group participation? Just like I can just look and see who's there and just call out your name. I think that's a good idea. I think you guys are probably thinking that's a terrible idea. And so I probably won't do that. But needless to say, the Ka that we got matches the Ka that they gave us. So we know that the X that we found was good. I need to go pick up children. So let's take a break. It might be 10, 15 minutes. Hang tight or don't hang tight and just watch the video at some point. Okay, guys? So I'll see you in a little bit. All right, guys, made it back. That actually didn't take that long. So that's pretty much a 10-minute break. Good. Okay, guys, so we left off with solving for the hydronium ion concentration, double checking it by putting it in an equilibrium expression and seeing if we get the same Ka that what was given. And then we also tried to assume X was small and found out that that just wasn't the case. Okay, so let's go to the next slide. That deals with now Kb. Kb is like Ka, only it's the base ionization constant. And instead of telling us the hydronium ion concentration, it tells us the hydroxide ion concentration. So same thing, same process, just tells us a little different information, okay? And this is what we use for bases. So with that in mind, do this problem and let's see what we get. Again, it's the same kind of thing, only we're now using Kb and finding hydroxide concentration. So what's the information we have? We have Kb. That would be .1. Okay. So hopefully you guys were able to rock out that ice table pretty quickly. We've done them enough now that they should hopefully become kind of second nature. And yeah. So now we just put this in our equilibrium expression, right? So 1.76 times 10 to the negative 5 equals x squared over 0.100 minus x. Let's just see if we can get rid of that x and not have to do the quadratic equation and all that stuff, okay? Let's do that. Multiply both sides by 0.1, we get 0.1 times 1.76 times 10 to the negative 5 equals x squared. And then we take the square root of that. And what do we get for x? Sorry, get out of the way. do you think? Anybody do that?
Point 0013.
Yeah, that's what I just got. Okay, so x equals 1.33 times 10 to the negative 3. Okay. Now what do? We've got our x, right? What's the next step?
Plug it into the E on the table.
Almost. But before we do that, we want to make sure to check, yes, that this a small x assumption is correct. Okay. So let's take this and divide it by 0.100, multiply by 100%. That should be what?
1.3.
1.3, yep. 1.3% is less than 5%, so we can proceed and now, as you said, plug that in for x. So 1.33 times 10 to the negative 3, 1.33 times 10 to the negative 3, 1.33 times 10 to the negative 3. What are they asking for in this question? They're asking for the hydroxide ion concentration and pH. We found the hydroxide ion concentration, it's X. How do we solve pH? Now, as was mentioned, if we wanted to check and make sure that that X was correct, we would plug it into the equilibrium expression. And if it equals 1.75 times 10 to the negative 5, then we know that we did it right. Okay. Let's just, for the sake of time, assume that that is correct. How would we find pH now that we have this being our OH?
Take the negative log of that and then subtract it from 14.
Yeah. Well, that, yes. So that is, what about, because remember it's pH, not POH. I mean, yes, if we want to find the POH, we could do that. And then take the difference, right? So what happens when you do that? Let's try that.
Uh, 2.88.
You get pH equals 2.
That's the POH. Sorry.
All right, yeah, POH. Okay. All right. And then we would say 14 minus 2.88 is 11.2. Yeah. Okay. That's one way to do it. What's another way to do it? this goes back to KW. What's KW equal? Right? And what is that equal to? Concentration of the hydronium times the concentration of the hydroxide. Right? So what happens when we take 1.0 times 10 to the negative 14 divided by 1.33 times 10 to the negative 3? Oops. We get our hydronium ion concentration being equal to 7.52 times 12. Okay. Now what? Let's take the negative log of that. And I get negative, so negative log, I'll write it out here, of this equals 11.12, which is pretty close to our 11.2. Okay. More than one way to skin a cat. And it's always good to do it another way if you can, to see if it all makes sense. Now, what would have been the final check or the check to do before this? As I said, plug in that X for the equilibrium concentrations and see if it equals that KB. Any questions on this, guys? Is this making sense? It might just take a little bit of practice, a couple times going through this, but hopefully by now we are getting to a point where this has some semblance of familiarity. Okay. I think that was the last problem on the slide deck. So now we're going to go into uncharted territory. Now we're just going to let's just do a few more practice problems and then we'll wrap it up. Okay. Call it a weekend. pH of a weak base solution. Okay. So they give us the hydronium ion, or they want us to find the hydronium ion concentration. That's the wrong title. That should be a weak acid solution. That must be why this is in my slide graveyard. I haven't gone over it with a fine-tooth comb. So calculating pH of a weak acid solution. It wants us to find the hydronium ion concentration. It gives us the concentration of the acid. It gives us the Ka. So all we need to do, ice baby, and go from there. All right. So if you want to stick around and work on these, please do. If you want to leave, go for it. Hydrocyanic acid going to hydronium plus cyanide. Concentration 0.1. This is 0. This is 0. So it's x plus x plus x. 0, 1, 0, 0 minus x. x, x, and then 4.9 times 10 to the negative 9 equals x squared, 0.100 minus x. Hopefully you guys that are still here are working on this, got this far. So what do we do from here, guys? What's the next step? Small x, yes. Small x, assumption. So let's just get rid of that small x. And so then this just becomes 0.1 times 4.9 times 10 to the negative 10 equals x squared. Take the square root, both sides, and what do we get when we crunch that? I'm getting 7 times 10 to the negative 6 equals x. Okay. Same on the chat. Awesome. Great. Now, next step, verify. Trust but verify. So we just take this number and we divide it by what we said it was not impacting, 0.100, and then multiply by 100%. So this number divided by 0.1 times 100, and I'll guarantee you, yeah, it's a very, very small percentage, not even 1%. So very, very confident that that small x assumption works. So 7.0 times 10 to the negative 6 is our x. What were they asking for again in this problem? Find the, okay. Yeah, all right. So cool, we're done. That is the hydronium ion concentration, right? X, this. So we stick a fork in that and we move on. Let's do one more problem. Share. Sharing is caring. Okay. Again, that should say weak base solution. I'm going to write it up here, but I really strongly encourage you guys to write it down on your own at your place and try to work along with us, okay? Okay, good. Finally, they give us something besides 0.1. I was getting sick of 0.1. All right. On our x's. That's looking good. Minus x. Okay. So hopefully you've gotten this far. I'm going to make this big. What's next? Our equilibrium expression, right? So 4.6 times 10 to the negative 4 equals x squared over 0.200 minus x. Small x assumption. So we go and we get rid of that. I don't know about you guys, but I grew up watching Bob Ross on Channel 9, not because I really wanted to, but because we only had like 5 channels. And so I had to watch it to, wait for the program that I really wanted to watch come on. But then I started to like it. And I remember he would always encourage, it's okay to make like little noises as you make brush strokes and stuff. That's perfectly natural. So sometimes I tend to make little noises too when I'm writing up here because I just feel like it makes it go along more easily. But if that's annoying, let me know and I'll try my best to shut up. Okay, multiply both sides by 0.200. Take the square root. And what do we get, guys? Negative 4 times 0.2. Square root of that. I'm getting 9.6 times 10 to the negative 3 equals x. Okay, let's make sure that that was a valid assumption. So we divide by 0.200, multiply by 100%. What do we get? Exactamundo. Now, 4.8 is close to 5, but it's not 5. So we can still make this assumption, but just barely make the assumption. Okay, so let's just roll with it. So if that's the case, what are they asking for in this problem again? They're asking for pH. Yeah, they're asking for pH. Okay. So what that means is 9.6 times 10 to the negative 3 is our hydronium ion concentration. So the pH would be the negative log of that, 9.6 times 10 to the negative 3. So what do we get there? Anybody? 2.2. Okay, pH is 2.02. Okay. Now, why not just for giggles? Why don't we plug that back in and see if it comes close to our 4.6 times 10 to the negative 4? Since we were just on the threshold of making that assumption confidently, we would say that Ka equals 9.6 times 10 to the negative 3 squared over 0.200 minus 9.6 times 10 to the negative 3. What happens when we get that? Squared divided by 0.2 minus. I get 4.8 times 10 to the negative 4. Yep. So do you, Chase. Right on. Okay, so 4.6, 4.8. Close enough for this, guys. And so we're good to go. pH 2.02. All right. Let's wrap it up there, because next week maybe we'll do some titration stuff, and then that's it for Chem 102, guys. You really are in the home stretch, which is exciting. It's a relief, maybe a little sad, but it depends on how you like or dislike this class. But anyway, have a great weekend. Send me your abstracts if you want. I will see you Tuesday, and until then, okay?